Okay, good morning. Here's the joke of the day. It's pretty much the theme for all of these jokes. Today we'll be going over the homework, which is a three-part nuclear reaction sheet. That should take about 5 minutes or so. Then we're going to learn about nuclear reactors and the risks involved with nuclear chemistry. And then you've got some homework for tonight. You do have a lab that is due today at 3:15, and the test on nuclear chemistry is going to be due Monday at 3:15. Okay? All right, the homework is here. The first part of this, all you had to do was tell whether it was a capture or not. And I think I did the first one for you. All of these are decays, okay? So really all you had to do is identify what the particle was that was being given off during the decay. So this one's a beta. So all of these are decays. So this is a beta decay. What's this one? That's an positron. We recognize this as an alpha particle. Remember, alpha particles are essentially helium atoms that have had their electrons stripped away, and because of that, they have a +2 charge. And when thorium gets converted into actinium, it's both, it gets rid of a beta particle and gamma radiation. Okay, so all of these are decays. All right, let's pull this up. I can erase these. Okay, so this is similar to what we've already done, so this shouldn't be too bad. 84, we have an alpha decay. And I just have to make sure that these are going to add up. So 212 and 4, that's 208. 82 plus 2 is 84. So we go from polonium into lead. Lead is 82, alpha decay. Okay, this is called promethium, and this gets converted into neodymium. And how do we do that? Well, this has got to be a +1, and there's no change in the mass, so that's a 0. So this is we show it as a symbol as an electron. This is a positron decay. Okay, third one, polonium. Okay, sometimes you see it as a B, yes? So both of these, whoops, not that one, but 0, -1. You might see that same thing as an electron, 0, -1. But you should recognize both. That's beta decay. And this has to be a number that's 1 higher than that. So 85 and -1 is 84. No change there. And 85 indicates that it is astatine. Boron getting converted into lithium. Okay, so I've got to add 1 here, so that's a +1. And this does not change. So hopefully you recognize that that is a positron. We could also see it written like this, a positron, 0, +1, or like this. Okay, sodium into neon. Well, this has got to be a +1, right? And this does not change. So we've got the same thing. It's a positron. All right, uranium. Uranium, and they're telling you, in this case, alpha and gamma decay. So here's the gamma. I shouldn't really show it like a real Y. It should be more like that. okay? And alpha. Alpha is a helium atom stripped of its electrons. So I have to account for this, 2, so that's a 90, and that's going to be 234. So 90 plus 2 is 92, that makes sense. 234 and 4, that's 238, and 90 is thorium. All right, argon. So that's a positive 1, so this has got to be 1 fewer. 17 plus 1 is 18, and that's a 0, so that's a 37. And chlorine is 17, and we recognize this as a positron. So hopefully you didn't find too much trouble with those. I'm going to move this up. These are good practice for table N. Move that up as much as I can. Okay, write the nuclear equation for the release of the beta particle by lead-210. Lead-210. Lead is 82, I believe, that we already saw up there. That's 82. And it's releasing a beta particle. So beta particles are kind of like electrons with no mass and a -1 charge. So 82, and that would be an 83. 83 and -1 is 82. No change here, that's 210. And what's 83? 83 turns out to be bismuth. You could look that up pretty easily. Okay? We have the nuclear equation for positron decay of thorium-232. Thorium-232. Thorium is 90. So we're decaying here a positron that's 0 and a +1, and then that ends up being 89. 89 plus 1 is 90. That does not change. The element that is 89 is, let's look quick. Actinium again. Actinium. Okay? And the last one here, write the nuclear equation for the gamma decay of cerium. Well, cerium is Ce, and Ce has a atomic number of 58. Now, since they only told you it was gamma, then it's just going to be a gamma, and then cerium. Now, this can happen. That means that this has too much energy, but this would be a more stable cerium. Chances are good that when you have a gamma decay, it's probably going to be accompanied by an alpha or a beta particle, but you don't know, or a positron. But at this point, just because of the way this is worded, you can't tell. You can't really tell. Okay, so hopefully you did well with those, and we will move on. We're going to be learning about nuclear reactors. All right, scan up. We should be pretty good with nuclear decay and half-lives. Yesterday we learned about nuclear fission, which is essentially taking an atom and blasting it with some sort of particle through a collider and having that break apart, and when it breaks apart it releases energy. And when that happens, neutrons are also released, which can cause a chain reaction and cause more of nuclei to split. And that continues for a long period of time depending on what kind of fuel you're using. This is the type of thing that is used in nuclear reactors, and it's controlled. It's completely surrounded by something that cools it, and that's going to heat up water essentially and make turbines run, and we'll see that in a second. So that's nuclear fission, splitting of nuclei. If you don't control it, it's what happens in nuclear bombs. And fission is what we use in nuclear plants today. You start essentially with something large nuclei, and end up with smaller nuclei. Fusion, on the other hand, is the goal of humans. If we had fusion reactions that worked, then we wouldn't need any other type of fuel, and there wouldn't be any waste products either. So this is a big area of research. They haven't got it to the point where they can do cold fusion, but I'm going to guess within my lifetime that they will, hopefully. Today we're going to be learning about breeder reactors. So the first thing I'd like to do is quickly go over what a regular reactor is. Nuclear reactor. And there are different kinds of nuclear reactors, but essentially they kind of work the same thing, same way. Basically, you've got these rods in here, and these rods contain radioactive material like uranium-238. And there are little tiny pellets in there, and this is a protective coat here that will not allow for the exposure of the radioactivity to the water. So if you wanted less energy, you could move this up, and when you move this up, less of this is exposed. If you want more energy, this gets moved down, so more of the rods are exposed to the water. Essentially what happens here is you've got, in this one, you've got water completely surrounding it. The water gets heated up to the point where it's making steam. Okay, water is continuously pumped through the system, and eventually the water gets dumped out into, in the case of the one on at 9 Mile, it gets dumped into Lake Ontario. And then the things that you see that are typical of nuclear reactors, that's just the cooling tower there, and that's steam coming off. So the majority of the steam is going to go through they channel it through a turbine. So let's look at a turbine quickly. A turbine can be a wind turbine. You can use the same setup for hydroelectric. In any case, you've got something moving through, and it has blades kind of like a fan. And when steam, in this case, comes through, it spins it. And when it spins it, just like if you were to have a small fan and you blew on it, it would cause the blades of the fan to move around. And when that happens, it turns this giant rod here, okay, which is attached to a huge cylinder. Now, here's how the electricity is generated. Essentially, this giant cylinder spins around a magnetic field. So you've got magnets here, which are stationary, and then you've got coiled wire cylinder. So this is got huge amounts of copper that is wound around, and then this inside part is going to spin because that inside column here is attached to this. So when this spins, it causes the coils, the giant cylinder, to spin around. And when it spins around and the giant magnets stay there, it generates electricity. That electricity is then sent to the power plant, okay, and then sent to you and me. All right, so that is a turbine generator. That can be through water, it can be through wind. It's the same idea. Something spins, so we have copper wire that's spinning compared to a stationary magnetic field, and that causes electricity to be generated. Okay, so, nope, this one here. Okay, so that is how electricity is generated in a reactor, a nuclear reactor. Now, breeder reactors are reactors designed to produce fissionable fuel. Most of the uranium, natural uranium, 99% of it is 238, but 235 is the fissionable fuel. Okay, so what this does is A breeder reactor is a little bit more efficient in that it doesn't have to have the pure 235 fissionable fuel. It can use other products that can be. So it converts the 238 to plutonium-239, which is also fissionable. So it's basically a slightly more efficient reactor than the other. So here's, it's getting blasted by neutrons to become plutonium-239. Right? Now, there seems to be a fair amount of controversy with that because plutonium is, and I really should change this, considered by most, by many I should say, as the most toxic, or toxic is the word, toxic of all known substances. In incredibly small amounts can cause cancer and have caused cancer in animals. So it's pretty controversial. Okay? All right. Lastly, what kind of risks are associated with nuclear energy? Well, of course, we could be exposed to radiation. Now, again, we are exposed to radiation in the electromagnetic field of radiation. It's heat is radiation, but we're talking about ionizing radiation. Ionizing radiation is that radiation that can cause damage to our DNA. This type of radiation can cause kill cells, certainly cause mutations to your DNA, which can eventually cause the death of the organism. Of course, there are also issues with storage and disposal. Eventually, these fuel rods are not going to have as much energy as they did. Over time, they lessen their energy because of their half-lives, and eventually we have to dispose of them. Where do we put them? Big question. And of course, as we said before, there are nuclear accidents, 3 big ones, and we've learned from each one of them. And God forbid, something happens where it gets sabotaged. Okay, some rogue nation might find a way to melt down one of the nuclear reactors that we have and cause some problems. Okay, so that's what we're gonna. That's what we learned today. We're done for that. The homework is. Don't forget your M&M lab is due today. The test on Monday, and let's see what the homework is. It's this one here. It's in your packet. Okay, it's just comparing nuclear fission with nuclear fusion. A couple check marks. Sample equation. Shouldn't take you more than about 10 minutes. Okay? See you tomorrow.